You stand beneath the night sky, and at first it feels empty. The darkness stretches wide and deep above you, like a great ocean turned upside down. Pinpricks of light shimmer across it, scattered without pattern, quiet and far away. You have seen this sky many times before. Perhaps you have walked home under it, or paused beside a window to watch it. It feels familiar. Gentle. Still. But tonight, you let yourself look a little longer. Your eyes adjust slowly, drinking in the dim light. More stars appear. What seemed like emptiness begins to fill. The darkness is not empty at all, it is simply patient. Each of those small lights is a star. And a star, you remember, is not a tiny spark. It is a sun. A vast sphere of glowing gas, burning through hydrogen, releasing energy that travels across unimaginable distances. Our own sun, the one that warms your face and grows the trees and stirs the winds, is just one of these countless lights. And if our sun has planets, worlds of rock and ocean and cloud, then perhaps many of those distant stars do too. This realization settles into you slowly. For most of human history, you would not have known this. The stars were fixed points, decorations on a cosmic ceiling. Beautiful, yes. But unreachable and alone. It is only in the past few decades that you have learned something extraordinary. Planets are common. When astronomers look carefully, they find them everywhere. A planet is not easy to see directly. It does not shine with its own light. It reflects the faint glow of its star, like a grain of dust caught in a spotlight. Across the vastness of space, that reflected light is almost nothing. And yet, with patience and careful instruments, you have learned to detect them. Thousands have already been found. Some are large, like Jupiter, swollen with gas and swirling storms. Others are smaller, rocky, more like Earth. Some circle close to their stars, completing an orbit in just days. Others wander farther out, moving slowly through long, cold years. The universe, you begin to understand, is not sparse. It is abundant. Imagine holding a handful of sand. Each grain presses softly against your skin. Now imagine that every grain is a world. This is closer to the truth than the old image of a lonely solar system floating in isolation. You are not standing beneath emptiness. You are standing beneath possibility. And the distances, though vast, no longer feel like barriers. They feel like invitations. Light travels quickly, faster than anything else in the universe. It moves at nearly 300,000 kilometers per second. Even so, the light from the nearest star beyond your sun takes more than 4 years to reach you. You are always seeing the past. The sky is a memory. When you look up, you are looking back in time. Some of the stars you see tonight may no longer exist as they appear. Their light began its journey long before you were born. It has been traveling silently through space, crossing interstellar clouds, slipping past wandering comets, until at last it reaches your eyes. There is something tender about that. The universe sends you messages constantly, and you receive them simply by looking. As you breathe in, you think about your own planet. Earth circles a star at just the right distance for liquid water to exist. Not too close, or oceans would boil away. Not too far, where everything would freeze. This narrow region is sometimes called the habitable zone, a gentle band of possibility around a star. It is not a promise of life. But it is an opening. If planets are common, and stars are common, then habitable zones must also be common. And within those zones, on some fraction of those worlds, conditions may settle into balance. Temperatures may soften. Atmospheres may gather. Chemistry may begin its quiet experiments. On Earth, life began early. Fossil evidence suggests that simple organisms appeared not long after the planet cooled enough for oceans to form. Life, it seems, does not always hesitate when conditions are right. You let that thought drift through you. If it happened here, could it happen elsewhere? The question is not loud. It does not demand an answer tonight. It simply rests beside you, like a companion. You imagine distant oceans under alien skies. Perhaps clouds form there, drifting across unfamiliar continents. Perhaps rain falls. Perhaps sunlight filters through atmospheres rich with strange chemistry. Perhaps somewhere, on a small rocky world orbiting a quiet star, simple cells divide and multiply, unaware that they are part of a vast cosmic pattern. Or perhaps not. Science does not assume. It listens. And so you have begun to listen to the stars. Not with your ears, but with telescopes. With instruments that measure tiny shifts in light. With sensors that detect changes so small they would have once seemed impossible to perceive. You are learning to notice the subtle signs that a planet is present, even when you cannot see it directly. It is like sensing someone in a dark room by the way the air moves. The night sky above you is no longer silent decoration. It is a field of potential signals. Each star may host worlds. Each world may have an atmosphere. And each atmosphere may carry chemical traces, clues about what is happening on its surface. You are only at the beginning of this search. For now, you stand beneath the sky and let its vastness settle gently into your thoughts. The fear that sometimes accompanies immensity begins to soften. You are not small in a meaningless universe. You are part of a living investigation. The atoms in your body were forged in ancient stars. The iron in your blood, the carbon in your cells, the oxygen you breathe, all were born in stellar furnaces long ago. When you look up, you are seeing your own origins scattered across the dark. The universe looks distant, but it is intimately connected to you. And as you continue to gaze upward, you begin to sense something else, a subtle reciprocity. You are observing the cosmos, yes. But in a way, it is also revealing itself to you, photon by photon, memory by memory. You look up. And the universe looks back. But how, exactly, do you detect a world that hides in the glare of its star? How do you notice something that refuses to shine? Perhaps the answer begins not with seeing the planet itself, but with noticing how its star gently moves. You might imagine a planet circling a star the way a moth circles a lantern, small, obedient, held in place by gravity's pull. The star, massive and radiant, seems unmoved by the tiny world that orbits it. But this picture is not quite true. In reality, gravity is never a one-sided force. It is a conversation. A mutual leaning. When a planet orbits a star, it does not simply travel around a fixed center. Both bodies orbit a shared point, called the center of mass. If the star is enormous and the planet is small, that shared point lies close to the star's center, but not exactly at its center. The star shifts, just slightly. It moves in response to the planet's pull. You imagine holding hands with someone much smaller than you and spinning gently in a circle. You would not stand perfectly still while they whirl around. You would both move, adjusting to each other's weight. Even if your motion were subtle, it would be real. Stars do the same. From far away, this movement is almost imperceptible. The star appears steady and fixed. But with careful instruments, you can detect its slow, rhythmic wobble, a tiny back-and-forth motion caused by the gravitational tug of an unseen planet. This method of discovery is called radial velocity. The name sounds technical, but the idea is simple. Radial refers to motion along your line of sight, toward you or away from you. Velocity is simply speed with direction. Together, they describe how quickly something moves closer or farther from where you are observing. As a star wobbles, sometimes it shifts slightly toward Earth. Sometimes it shifts slightly away. These motions are minuscule, often just a few meters per second. Slower than a running human. And yet, across light years of space, you can measure them. How? Through light. When a star moves toward you, its light is compressed slightly. The wavelengths become shorter, shifting toward the blue end of the spectrum. When it moves away, the wavelengths stretch, shifting toward red. This effect is called the Doppler shift, the same principle that makes a passing ambulance siren sound higher in pitch as it approaches and lower as it recedes. Light behaves like sound in this way. Motion leaves a fingerprint in its frequency. You cannot see the wobble with your eyes, but you can read it in the color of the starlight. The changes are extraordinarily small. The shift in wavelength may be just a fraction of a nanometer. Detecting it requires spectrographs, instruments that spread starlight into its component colors with exquisite precision. They measure tiny variations again and again, night after night, watching for a pattern. And when a pattern repeats forward, backward, you begin to suspect a planet is there. You never see the planet directly. It remains hidden in the glare of its star. But its gravity leaves a signature. A rhythm. A steady, repeating sway. The first confirmed detection of a planet orbiting a sun-like star was made this way in 1995. Astronomers observed a subtle wobble in the star 51 Pegasi. The movement was small but consistent. Something was tugging at it. That something turned out to be a planet later named 51 Pegasi b, orbiting very close to its star. It was a revelation. Since then, hundreds of planets have been discovered through radial velocity measurements. Some are massive, exerting strong pulls that make their stars sway more dramatically. Others are smaller, causing gentler motions that require even greater patience to detect. The size of the wobble tells you something important. A larger planet creates a stronger gravitational tug, producing a bigger shift in the star's motion. The timing of the wobble reveals the length of the planet's orbit, how long it takes to circle its star once. From this delicate dance, you can infer mass and distance. It is astonishing, when you think about it. You are reading the presence of a world not by seeing it, but by noticing how it moves another object. You are learning about distant planets by studying the subtle hesitation in a star's path. It is like inferring the existence of wind by watching leaves tremble. And there is something deeply calming about this method. It reminds you that not all knowledge comes from direct sight. Sometimes, truth reveals itself indirectly, through influence and response. Gravity, invisible yet universal, connects everything with mass. It is the quiet architect of cosmic structure. It shapes galaxies, sculpts solar systems, guides comets, and holds planets in their steady courses. You feel it constantly, pressing your feet to the ground, anchoring you gently to Earth. Out there, light years away, gravity is at work in the same way. You imagine a distant star, glowing steadily in the darkness. Around it, an unseen planet circles faithfully. The star shifts slightly in reply, a slow, patient wobble. Across the vastness of space, photons carry that information toward Earth. Years later, those photons enter a telescope, pass through lenses and mirrors, and land on a detector. And in that data, you see the sway. There is humility in this process. The measurements are careful. The conclusions are cautious. Astronomers observe the pattern over many cycles, ensuring it is not noise, not random fluctuation, not the star's own turbulent surface activity. They test and retest, aware that certainty must be earned. Because stars are not perfectly calm. Their surfaces churn with magnetic storms and convection currents. These can mimic or obscure the signals of orbiting planets. The challenge is to distinguish true gravitational motion from stellar restlessness. So you listen longer. And as instruments improve, becoming more stable, more sensitive, you detect smaller and smaller wobbles. Planets closer in size to Earth begin to reveal themselves. The dance grows more intricate. You begin to appreciate that the universe does not hide its secrets out of cruelty. It simply requires patience, attention, sensitivity to subtle change. The radial velocity method teaches you to look for influence rather than appearance, to notice motion rather than form, to understand that even the largest stars are not solitary monarchs, but participants in a shared gravitational embrace. Somewhere out there, at this very moment, countless stars are swaying gently in response to their planets. The dance never stops. You sit with a star. Not in person, of course. The star is impossibly far away, suspended in the dark like a lantern hung in an endless hall. But through a telescope, through careful measurement, you keep it company. Night after night, you watch its light. At first, the star seems steady. Its brightness appears constant, a reliable glow against the black canvas of space. But you are not simply admiring it. You are measuring it. Recording its intensity with quiet precision, letting detectors count each arriving photon like grains of luminous sand. And then, almost imperceptibly, the light dips. It is not dramatic. The star does not flicker like a candle in wind. The change may be less than 1%, a tiny decrease in brightness that lasts for a few hours, then returns to normal. If you were not watching carefully, you would never notice. But you are watching carefully. This brief dimming is called a transit. A planet, in its steady orbit, passes directly between its star and your telescope. For a short time, it blocks a small fraction of the starlight. It casts a shadow across space, and that shadow reaches you as a subtle reduction in brightness. You imagine holding a coin in front of a distant street lamp. The lamp still shines around the edges, but its light is slightly diminished. If someone far away were measuring that light with extreme precision, they would see a small dip as the coin crosses. That is what you are seeing, except the coin is a planet, and the lamp is a star many light years away. The transit method depends on alignment. The planet's orbit must be tilted just right from your point of view. If the orbit is angled slightly above or below your line of sight, the planet will never pass in front of the star as seen from Earth. Most planetary systems are invisible to this technique. But when the alignment is perfect, the signal is clear. The depth of the dip tells you something important. A larger planet blocks more light, creating a deeper dimming. A smaller planet produces a shallower one. From the amount of light lost, you can calculate the planet's size relative to its star. It is astonishing, really. From a tiny shadow, you measure the radius of a world. The timing of the transits tells you even more. If the dip repeats at regular intervals every few days, or every few months, you know the planet is orbiting. The period between transits reveals the length of its year. Using the laws of gravity, you can then estimate how far it lies from its star. Light becomes a clock, a ruler, a storyteller. You begin to see that brightness is not static. It carries information. The steady glow of a star is like a calm lake. When something passes across it, even gently, ripples appear. One of the most transformative missions to use this method is NASA's Kepler Space Telescope. For years, Kepler stared at a single patch of sky, monitoring over 150,000 stars simultaneously. It did not move much. It simply watched. And in watching, it discovered thousands of planets. Each light curve, a graph of brightness over time, became a kind of heartbeat. Flat, steady lines interrupted by periodic dips. Some shallow and quick. Others deeper and slower. Each pattern representing a distant world crossing its star. You imagine scrolling through those light curves. Each one a quiet signal. Each dip a whisper, there is something here. The transit method has revealed planets of astonishing variety. Giant gas worlds that skim the surfaces of their stars. Rocky super-Earths larger than your own planet. Compact systems where multiple planets transit in delicate sequence, like beads sliding across a string. And when multiple planets transit the same star, their gravitational interactions can subtly shift the timing of each transit. These variations allow you to estimate their masses, adding weight to the silhouettes you detect. So from shadow and rhythm, you begin to reconstruct entire systems. There is something poetic about this. You are learning about solid worlds from absence, from missing light. The planet announces itself not by shining, but by blocking. And yet, This blocking offers more than size and orbit. When a planet transits, a small fraction of starlight passes through its atmosphere before reaching you. That light interacts with the gases surrounding the planet. Certain wavelengths are absorbed. Others pass through. If you analyze the starlight during a transit with a spectrograph, you may detect faint signatures imprinted by the planet's atmosphere. It is as if the shadow has texture. Imagine sunlight streaming through stained glass. The colors that reach the floor are shaped by the glass itself. In the same way, the atmosphere of a transiting planet filters starlight, leaving chemical fingerprints in the spectrum. These fingerprints can reveal the presence of gases like hydrogen, sodium, water vapor, even methane or carbon dioxide. The signals are faint. They require repeated observations and careful analysis. But they are real. You begin to realize that a transit is not just a dimming. It is an opportunity. Through this brief alignment, you glimpse the edge of another world's sky. Of course, the method has limits. It favors planets close to their stars, because they transit more frequently and produce more detectable signals. It depends on geometry, on chance alignment. Many worlds remain unseen because they never cross our line of sight. But the ones that do cross leave clear marks. You imagine a distant observer watching Earth from afar. Every year, our planet would pass in front of the sun from their perspective. The sun's brightness would dip slightly, less than 0.01%. If that observer were patient, precise, and curious, they would detect our transit. They would know our size, our orbital period, our distance from the sun. And if they studied the sunlight filtering through our atmosphere during transit, they might detect oxygen, water vapor, methane. They might begin to wonder about us. The thought is gentle, not alarming. It is simply a reminder that detection works both ways. The same methods you use to find distant worlds could, in principle, reveal your own. For now, though, you remain the observer. You sit with the star and watch its light dip and rise again. Dip and rise. Each cycle a confirmation. Each shadow a quiet announcement. You have watched the shadow of a planet pass across its star. You have seen the faint dip in brightness, the gentle blink that tells you a world is there. But now you lean closer, not to the planet's surface, not to its oceans or mountains, which remain hidden, but to something softer and more revealing. Its air. When a planet transits its star, most of the starlight travels past it unchanged. But a very small portion passes through the thin rim of atmosphere that surrounds the planet. Before that light reaches your telescope, it must travel through layers of gas, through molecules drifting and colliding in an alien sky. And as it passes through, something subtle happens. Certain colors of light are absorbed. To understand this, you imagine sunlight streaming through a prism. The white beam splits into a rainbow: red, orange, yellow, green, blue, violet. This spread of colors is called a spectrum. It reveals that white light is not simple, but composed of many wavelengths blended together. Now imagine that this rainbow passes through a cloud of gas. The atoms and molecules in that gas do not absorb all colors equally. Each type of molecule interacts with light in a specific way. They absorb particular wavelengths, corresponding to the energies of their internal vibrations and electron transitions. The result is a spectrum with missing lines, dark gaps where certain colors have been removed. These gaps are not random. They are fingerprints. Every molecule leaves a distinct pattern of absorption lines. Oxygen absorbs at particular wavelengths. Water vapor at others. Methane, carbon dioxide, sodium each has its own spectral signature. When you observe a star during a planetary transit and spread its light into a spectrum, you can compare the starlight before, during, and after the transit. If certain wavelengths are slightly dimmer during the transit, you know that something in the planet's atmosphere is absorbing them. It is as if the planet's sky signs its name in light. This technique is called transmission spectroscopy. The term sounds technical, but you can think of it simply as reading the filtered light that is transmitted through an atmosphere. The signals are incredibly faint. The planet blocks only a small fraction of starlight, and the atmosphere is just a thin shell around that planet. The additional absorption caused by atmospheric gases may change the star's brightness by only a few parts per million. And yet, with careful instruments and repeated observations, you can detect it. You imagine the patience required. Astronomers may observe dozens of transits, stacking the data together to reduce noise. They must correct for fluctuations in the star's own light, for interference from Earth's atmosphere if observing from the ground, for instrumental drift. It is delicate work. But when the signal emerges, when the pattern of absorption lines aligns with known molecular fingerprints, it is profound. You have detected the chemistry of a distant sky. Already, you have found atmospheres rich in hydrogen, surrounding large gas giants. You have detected sodium in scorching hot exoplanets orbiting close to their stars. Water vapor has been observed in the atmospheres of several distant worlds, its spectral features faint but unmistakable. Water. Even when it exists as vapor high above a planet's surface, its presence captures your imagination. On Earth, water shapes climate, carves landscapes, sustains life. To detect its signature in the light of another world feels like glimpsing a familiar word in an unfamiliar language. But chemistry is not just about individual molecules. It is about combinations. Some gases can exist together easily. Others react quickly and would disappear unless something continually replenishes them. On Earth, for example, oxygen and methane coexist in the atmosphere. Yet chemically, they should react and neutralize each other over time. Their simultaneous presence is not equilibrium. It is imbalance. An imbalance can be a clue. You begin to see that reading a spectrum is not just about listing ingredients. It is about understanding relationships. If you detect carbon dioxide alone, that tells you something. If you detect water vapor alone, that tells you something else. But if you detect oxygen alongside methane in substantial quantities, your curiosity sharpens. Because on Earth, that particular pairing is sustained by life. Plants and photosynthetic microbes release oxygen. Other organisms produce methane. Without biological processes constantly renewing them, those gases would not persist together. This is what scientists call a biosignature, a chemical pattern that may indicate biological activity. But you move gently here. You do not leap to conclusions. The universe is complex. There may be geological or photochemical processes that produce similar imbalances under certain conditions. You must consider alternatives. You must model atmospheres carefully, simulate climates, test hypotheses. Still, the possibility lingers. You imagine a distant telescope observing Earth during a transit across the Sun. The observer would detect nitrogen, oxygen, water vapor, traces of methane. They might see ozone, a molecule formed when ultraviolet light interacts with oxygen. They would not see forests or oceans directly. But the spectral fingerprints would hint at a dynamic, chemically active world. In this way, atmospheres become storytellers. They speak of volcanic activity, of stellar radiation, of surface temperatures. They reveal whether a planet retains its air or has lost it to space. They hint at clouds and hazes that scatter light in complex ways. Some atmospheres are thick and heavy, rich in hydrogen and helium, swelling far above the planet's surface. Others may be thin, like Mars, fragile and easily stripped by stellar winds. Some may be dominated by carbon dioxide, trapping heat in a greenhouse embrace. Each combination shapes the climate below. As you think about this, you realize that you are not just searching for life. You are searching for context. For environments. For conditions that allow chemistry to become intricate, layered, sustained. The spectrum is your guide. Modern space telescopes, positioned beyond Earth's atmosphere, are especially powerful for this task. Freed from the distortions of air and weather, they can detect infrared wavelengths where many important molecules absorb light. In these wavelengths, the universe glows differently. Cooler objects emit more strongly. Atmospheric features stand out more clearly. You imagine photons leaving a distant star, passing through a planet's atmosphere, carrying subtle imprints across light years. When they finally reach a telescope mirror, they are captured, focused, analyzed. The data appears as lines and curves on a screen. From that quiet graph, you infer wind, temperature, chemistry. It feels almost intimate. You are reading the breath of another world. And yet, you know how careful you must be. Noise can masquerade as signal. Instrumental effects can mimic absorption lines. Stellar activity, flares, spots, magnetic cycles can alter spectra in ways that complicate interpretation. So you verify. You observe again. You compare models. You consult independent instruments. Science moves slowly here, as it should. But even with caution, the progress is remarkable. Only a few decades ago, you did not know whether planets existed around other sun-like stars. Now you are probing the composition of their atmospheres. From shadow to chemistry. From dimming light to molecular identity. You feel a quiet awe at how far perception has extended. Human eyes cannot resolve these distant worlds. But human curiosity, amplified by technology, can. And as you rest with this thought, another question begins to rise, not about distant atmospheres, but about your own. If certain chemical imbalances hint at life elsewhere, what does the air around you say about this planet? What signature does your own breath leave behind? Perhaps the next step in understanding distant worlds is to look inward first, and listen to the chemistry of life as it surrounds you now. You begin with a breath. It happens so quietly that you rarely notice it. Air enters your lungs, expands your chest, and leaves again in a soft, invisible tide. Inhale. Exhale. A rhythm so constant it fades into the background of awareness. But tonight, you linger with it. The air you draw in is mostly nitrogen. Nearly 78%. Oxygen makes up about 21%. The remaining fraction includes argon, carbon dioxide, traces of methane, water vapor, and other gases in small amounts. It seems ordinary. Familiar. And yet, this mixture is extraordinary. Oxygen is highly reactive. It bonds eagerly with other elements. Left to chemistry alone, free oxygen in a planet's atmosphere tends to disappear. It combines with rocks, with metals, with volcanic gases. Over time, it should be consumed. And yet here it is, abundant and persistent. Why? Because life is constantly renewing it. On Earth, microscopic organisms in the oceans, along with plants on land, perform photosynthesis. Using sunlight, water, and carbon dioxide, they produce oxygen as a byproduct. Every leaf that unfurls, every phytoplankton cell drifting near the ocean's surface, participates in this quiet transformation of light into breath. You inhale the result. The oxygen entering your body tonight is part of a planetary cycle billions of years old. It has moved through forests and coral reefs, through lungs and gills, through flames and rusting iron. It is not static. It is dynamic, continuously produced and consumed. This dynamic balance is called disequilibrium. In chemistry, equilibrium is a state of balance, where reactions proceed forward and backward at equal rates. The composition of the system remains stable without outside input. But Earth's atmosphere is not in simple chemical equilibrium. It is actively maintained. Oxygen coexists with methane, even though they react readily with each other. Nitrous oxide lingers despite processes that could remove it. Ozone forms and breaks apart in cycles shaped by ultraviolet light. This mixture is unstable in a purely chemical sense. It should settle into something simpler. Something quieter. But life keeps stirring it. You begin to understand why scientists search for atmospheric disequilibrium when studying exoplanets. It is not just the presence of a single molecule that matters. It is the relationship between molecules, the persistence of combinations that should not endure without constant replenishment. Imagine walking into a room and finding a candle burning. The flame is not permanent. It requires fuel and oxygen. If you see the flame, you know something is actively sustaining it. It is not a relic of the past. It is happening now. In the same way, certain atmospheric compositions may indicate ongoing processes. Oxygen alone is intriguing, but not definitive. There are ways to produce oxygen without life through the photodissociation of water vapor, for example, when ultraviolet light splits water molecules and hydrogen escapes into space. Over time, this can leave oxygen behind. So you must be cautious. But oxygen combined with methane, maintained in significant quantities over long periods, becomes harder to explain without biology. On Earth, methane is produced largely by microorganisms that thrive in low-oxygen environments, in wetlands, in the guts of animals, in sediments beneath the sea. Methane breaks down relatively quickly in an oxygen-rich atmosphere. Its continued presence suggests constant renewal. This pairing oxygen and methane together is one example of a potential biosignature. You breathe in again. Your body itself is a chemical system far from equilibrium. Cells constantly convert oxygen and glucose into energy, producing carbon dioxide and water. If these reactions stopped, equilibrium would arrive, but so would stillness. Life resists equilibrium. It maintains gradients, differences in concentration, differences in temperature, differences in charge. Your cells pump ions across membranes to create electrical potentials. Your blood carries oxygen from lungs to tissues, maintaining contrast between what is rich and what is depleted. You are a network of imbalances, carefully regulated. On a planetary scale, life does something similar. It shapes the atmosphere, the oceans, the soil. It moves carbon from air to rock and back again. It alters albedo, the reflectivity of the surface, through forests and ice cover. It changes the chemistry of rain and river. If an alien observer studied Earth's spectrum during a transit, they would see more than isolated gases. They would see patterns sustained over time. They would see variability tied to seasons, subtle shifts in carbon dioxide as plants grow and wither. They might detect chlorophyll's spectral edge, the sharp increase in reflectance from vegetation at certain wavelengths. They would not see you directly, but they would sense activity. You imagine that distant observer patiently gathering data over decades, watching for consistency, testing hypotheses, asking whether geology alone could explain what they see. The search for biosignatures on exoplanets follows the same careful path. Scientists build atmospheric models, simulate chemical reactions under different stellar conditions, and explore non-biological scenarios. They examine how ultraviolet radiation from various types of stars influences atmospheric chemistry. Because stars differ. A small, cool red dwarf star emits light differently than a sun-like star. Its ultraviolet output may drive distinct photochemical pathways, potentially creating oxygen or ozone without life. So context matters. The planet's mass matters too. A small planet may struggle to retain its atmosphere, losing lighter gases to space. A larger one may hold onto thick hydrogen envelopes that obscure surface conditions. Temperature matters. Pressure matters. Geological activity matters. You see now that detecting life is not a single measurement. It is a tapestry of evidence. And yet, it begins with something as simple as breath. You inhale again, slowly. The oxygen you draw in tonight is a signal not intentionally sent, but unmistakably present. It accumulates in your atmosphere because countless organisms are engaged in the quiet labor of photosynthesis. Your planet's air tells a story of metabolism on a global scale. When you think of it this way, Earth feels less like a static sphere of rock and more like a living system, dynamic, self-modifying, responsive. The term biosphere captures this idea. It refers to the global sum of all ecosystems, every forest, every reef, every microbe interacting with the atmosphere, hydrosphere, and lithosphere. Together, they shape planetary chemistry. Life is not just on Earth. It is woven into Earth. And so, when you search for biosignatures elsewhere, you are searching for signs that another planet's chemistry has been similarly transformed. That its atmosphere is not merely the passive result of volcanic outgassing or stellar radiation, but something actively maintained. You know the challenge is immense. The signals are faint. The interpretations are delicate. False positives exist. Unfamiliar chemistries may surprise you. But you also know this: life leaves traces. It alters its environment in order to survive, and in doing so, it becomes detectable. You let your breathing slow, feeling the rise and fall of your chest. Each inhale is a reminder that you live on a world shaped by biology. Each exhale releases carbon dioxide that plants will use again. The cycle continues, vast and intimate at once. And as you consider distant planets with unfamiliar skies, you begin to wonder what other forms of disequilibrium might signal life there. What combinations of gases, what subtle imbalances, might reveal processes stranger than anything you know? To answer that, you must first understand the incredible diversity of worlds themselves, the fiery giants, the frozen wanderers, the rocky spheres in between, because not all planets are shaped alike, and not all skies breathe the same. You have been listening to atmospheres, searching for breath. But before you can decide whether a distant sky might carry signs of life, you must understand the worlds that hold those skies. And as you begin to explore the catalog of known exoplanets, you discover something humbling. The universe does not repeat itself neatly. When the first exoplanets were discovered, many of them defied expectation. Astronomers had assumed that other solar systems would resemble your own small rocky planets near the star, large gas giants farther out. That pattern made sense because it is what you know. But the cosmos had other ideas. Some of the earliest detected planets were what you now call hot Jupiters. These are gas giants similar in mass to Jupiter, yet they orbit astonishingly close to their stars, sometimes completing a full orbit in just a few days. Instead of dwelling in cold outer regions, they skim the stellar surface. Imagine Jupiter pulled inward until it glows under intense radiation, its clouds heated to thousands of degrees. On some of these worlds, temperatures are high enough to vaporize metals. Winds may race at thousands of kilometers per hour, redistributing heat from the permanently lit side to the dark. Because many hot Jupiters are tidally locked, one side always faces the star, bathed in relentless daylight, while the other remains in perpetual night. The boundary between them, the terminator, may host extreme temperature gradients, with atmospheric gases flowing violently across hemispheres. These are not gentle places. And yet they teach you something important: planetary systems are dynamic. Gas giants can migrate inward after formation, reshaping their systems. Orbits can shift. Worlds can move. Beyond hot Jupiters, you find super-Earths, planets larger than Earth but smaller than Neptune. These worlds do not exist in your own solar system, yet they appear common elsewhere. Their compositions may vary. Some may be rocky with thick atmospheres. Others may be ocean worlds, covered entirely by deep global seas. Imagine standing on a world where there is no land, only water stretching endlessly beneath a dense sky. Beneath the ocean's surface, pressures climb, perhaps forming exotic layers of high-pressure ice even though temperatures remain above freezing at the top. Then there are mini-Neptunes, smaller versions of Neptune, wrapped in thick hydrogen-helium envelopes. These planets may have rocky cores hidden beneath vast layers of gas, their surfaces unreachable and their atmospheres crushing. And farther out, you find cold giants and icy worlds orbiting at great distances from faint stars. Their surfaces may be frozen solid, their atmospheres thin or absent. Some may resemble the outer moons of your own solar system, but on a planetary scale. The diversity is breathtaking. You begin to realize that temperature alone does not determine habitability. A planet might orbit within its star's so-called habitable zone, the region where liquid water could exist yet still be hostile. If its atmosphere is too thin, water would evaporate or freeze easily. If too thick, a runaway greenhouse effect could raise surface temperatures beyond survivability. You think of Venus. Venus is similar in size to Earth and lies near the inner edge of the Sun's habitable zone. Yet its thick carbon dioxide atmosphere traps heat so efficiently that surface temperatures exceed 460 degrees Celsius. Lead would melt there. The pressure at the surface is more than 90 times that of Earth's. Proximity alone does not guarantee comfort. Mars, by contrast, lies near the outer edge of the habitable zone. Evidence suggests it once had flowing water, rivers, and perhaps oceans. But its small size allowed much of its atmosphere to escape into space. Without sufficient atmospheric pressure, liquid water cannot remain stable on the surface for long. Mass matters. A planet must be large enough to retain an atmosphere over billions of years, yet not so large that it becomes enveloped in thick hydrogen layers like a mini-Neptune. Gravity shapes the long-term fate of air. Radiation matters too. Stars vary in activity. Young stars, especially small red dwarfs, can emit powerful flares and intense ultraviolet radiation. Such radiation can erode atmospheres or alter their chemistry dramatically. A planet may orbit within a habitable zone but be subjected to stellar storms that challenge the persistence of life. Magnetic fields play a role as well. On Earth, the magnetic field deflects much of the solar wind, helping protect the atmosphere from gradual stripping. Without such shielding, a planet's air may slowly drift away. You begin to see habitability as a delicate balance, a choreography of factors. Distance, mass, atmosphere, magnetic field, stellar behavior, geological activity, all interacting. And then there is water. Liquid water is central because it is an excellent solvent. It allows complex chemistry to unfold. It moderates temperature. It participates in cycles that regulate climate. But water's presence depends on pressure and temperature conditions that must align. Too hot, and oceans boil into steam. Too cold, and they freeze solid. Too little pressure, and liquid water cannot remain stable. Too much greenhouse gas, and the surface overheats. You imagine the narrowness of these constraints. Not impossibly rare, perhaps, but certainly specific. Yet you also remind yourself that life on Earth thrives in extremes. Microorganisms inhabit deep-sea hydrothermal vents, acidic lakes, polar ice, and arid deserts. Extremophiles tolerate temperatures and pressures that once seemed incompatible with life. Perhaps habitability is broader than you first assume. Still, there are limits. A gas giant like Jupiter, with no solid surface and immense pressures in its interior, seems unlikely to host Earth-like life in its clouds, though speculation continues. A tidally locked hot Jupiter with molten dayside temperatures likely does not offer stable surface conditions. The diversity of worlds forces humility. You cannot assume that Earth is the template for all life. But you can use it as a starting point, a reference for what chemistry looks like when biology flourishes. As you move through this catalog of worlds, you feel a quiet awe. The cosmos is creative. It produces configurations you had not anticipated. It assembles systems unlike your own. And yet, within that diversity, you search for patterns. For planets roughly Earth-sized. For those orbiting within temperate zones. For atmospheres that are not too thick, not too thin. You begin to appreciate that finding a truly Earth-like world may be rare, not because planets are rare, but because the combination of factors that produce long-term stability might be uncommon. Rare does not mean unique. It simply means precious. You let that thought settle. The search is not for perfection. It is for possibility. A world does not need to mirror Earth exactly to host life. It only needs the right conditions for chemistry to become self-sustaining, to maintain disequilibrium over time. And somewhere among the billions of stars in your galaxy, there may be planets where fire and ice give way to temperate balance, where oceans reflect starlight and atmospheres carry subtle signs of ongoing processes. But to narrow the search, you return to a simpler idea, a region around each star where conditions might allow liquid water to exist. A narrow band. A zone of maybe. And within that thin ring of possibility, you continue your patient listening. You arrive at a simple idea. A planet that is not too hot. Not too cold. A world where liquid water can exist on the surface, where it can pool, flow, evaporate, and fall again as rain. This region around a star is often called the habitable zone. Some call it the Goldilocks zone, after the old story of something being just right. It is the range of distances where a planet could, in principle, maintain temperatures suitable for liquid water. But you already know something important. Could is not the same as will. The habitable zone is not a promise. It is an invitation. To understand it, you imagine a star radiating energy in all directions. The closer you move to it, the more energy you receive. Step too near, and oceans would boil into vapor. Move too far away, and water would freeze into ice. Between these extremes lies a band, a region where, if conditions align, water may remain liquid. For a star like your Sun, Earth sits comfortably within this band. Venus lies closer to the inner edge, and Mars nearer the outer edge. But as you learned before, location alone does not determine outcome. Venus, though near the habitable zone, experienced a runaway greenhouse effect. Thick carbon dioxide trapped heat so effectively that temperatures soared beyond survivability. Mars, though once warmer and wetter, lost much of its atmosphere and now sits cold and dry. The habitable zone defines potential, not destiny. Now you consider other stars. Stars vary in brightness and temperature. A large, luminous star emits far more energy than the Sun. Its habitable zone lies farther out. A small red dwarf star emits less energy, so its habitable zone sits much closer in. This shift changes more than distance. Around red dwarfs, which are the most common type of star in the galaxy, the habitable zone may be so close that planets there become tidally locked. One side always faces the star, the other always faces away. Day and night are permanent hemispheres. Would such a world be habitable? You imagine standing at the boundary between endless daylight and eternal night. Perhaps winds circulate heat from one side to the other. Perhaps oceans redistribute warmth. Perhaps a ring of temperate conditions forms along the twilight zone. Climate is not static. It is dynamic. And here, atmosphere becomes everything. A planet's atmosphere acts like a blanket. It traps heat through the greenhouse effect, allowing surface temperatures to rise above what they would be from stellar radiation alone. Without greenhouse gases like carbon dioxide, water vapor, and methane, Earth would be frozen solid. But too much greenhouse effect leads to overheating. The balance is delicate. You think of clouds. They reflect sunlight back into space, cooling the planet. But they also trap infrared radiation, warming it. Their overall effect depends on altitude, thickness, composition. You think of oceans. Water absorbs and stores heat, moderating temperature swings between day and night, between seasons. Currents transport warmth across latitudes. You think of ice. Ice reflects sunlight efficiently. If ice spreads, it can increase reflectivity and cool the planet further, a feedback loop. If ice retreats, darker surfaces absorb more heat, accelerating warming. Climate is a web of interactions. So when scientists define a habitable zone, they must make assumptions about atmospheric composition, about cloud behavior, about surface pressure. Different assumptions shift the boundaries slightly inward or outward. There is no single line marking safety. You begin to see the habitable zone as a gradient rather than a border. Some regions may allow stable oceans for billions of years. Others may permit temporary warmth before freezing or overheating. Geological activity may replenish greenhouse gases through volcanic outgassing, while weathering processes draw them down. On Earth, plate tectonics plays a role in long-term climate regulation. Carbon dioxide released by volcanoes enters the atmosphere. Rain dissolves carbon dioxide and helps form carbonate rocks, locking carbon away. Over millions of years, this cycle stabilizes temperature. Would an exoplanet need plate tectonics to remain habitable? Perhaps. Or perhaps other mechanisms could suffice. You feel the complexity deepen. The habitable zone is a starting filter, a way to narrow billions of planets down to those worth closer examination. It tells you where to focus telescopes, where to listen more carefully for atmospheric signals. But you know better than to assume that every planet in this band hosts life. Some may be barren despite their location. Others just outside the classical zone might host subsurface oceans warmed by internal heat, like Jupiter's moon Europa. Life, if it exists, may not always require surface oceans under starlight. Still, liquid water on a surface remains one of the most promising indicators of habitability as you understand it. You imagine plotting stars on a diagram, drawing thin rings around them, shifting in size depending on luminosity. Around some stars, the ring is wide. Around others, narrow. Around the hottest stars, the habitable zone may exist only briefly before the star evolves. Around smaller stars, it may persist for tens of billions of years. Time matters too. A planet may enter or leave the habitable zone as its star brightens over time. Your own sun grows gradually more luminous as it ages. In the distant future, Earth may drift toward the inner edge of the habitable zone, facing increasing heat. Habitability is not fixed. It evolves. You feel a quiet reverence for the present moment. Earth resides within a narrow window, spatially and temporally, where conditions allow life to flourish. This window has remained open for billions of years, long enough for complexity to arise. How many other windows exist in the galaxy? Statistical studies suggest that Earth-sized planets within habitable zones are not exceedingly rare. Many red dwarf stars appear to host rocky planets within their temperate regions. The numbers hint at abundance. But numbers alone do not reveal atmosphere, or ocean, or chemistry. That requires deeper listening. You return to the idea of balance, not too hot, not too cold. But you now understand that balance emerges from interaction. From greenhouse gases, clouds, oceans, geology, stellar radiation. A planet in a habitable zone is like a seed planted in fertile soil. Conditions may be favorable. But whether life takes root depends on many subtle factors. And so the search continues. You imagine future telescopes focusing on small rocky planets within these narrow bands, measuring their spectra, searching for oxygen, methane, carbon dioxide in meaningful combinations. The habitable zone narrows the field. The atmosphere tells the story. You rest with this layered understanding. The cosmos offers many worlds of fire and ice. Among them are rings of possibility, thin bands where liquid water might persist. Within those bands, some planets may achieve the delicate balance required for long-term stability. And somewhere, perhaps, a world hovers at just the right distance from its star, wrapped in a protective atmosphere, oceans glinting beneath drifting clouds. To find it, you will need instruments sensitive enough to taste the faintest traces of light, telescopes that can separate a planet's whisper from its star's roar. You step into a room filled with silence, though it hums softly with energy. Mirrors, lenses, detectors, instruments of incredible delicacy dominate the space. They are not flashy. They do not glow. Their purpose is subtle, to taste starlight. To extract meaning from the faintest photons that have traveled unimaginable distances. You imagine a photon leaving a star hundreds of light years away. It departs in a straight line, continuing its journey across the void, past wandering dust clouds, past magnetic fields, past other stars. Eventually, it reaches Earth. Every photon counts. Some telescopes sit on the ground, on mountain peaks where the air is thin and still. Others soar beyond the atmosphere, orbiting Earth, free from the distortions of air and weather. There, the instruments encounter less noise, fewer obstacles. They capture light in ultraviolet, visible, infrared wavelengths that are absorbed or scattered by Earth's atmosphere and would otherwise never reach the surface. You see the telescope as more than glass and metal. It is an extension of human curiosity, reaching out to touch distant worlds indirectly. It allows you to measure light that has spent centuries on its journey, preserving a message written long before your existence. The challenge is immense. Stars shine intensely, while planets orbiting them are dim by comparison. A star can outshine its planet by thousands or millions of times. The planet's signal is a subtle pattern, a whisper in the stellar roar. To detect it, astronomers employ precision and patience. They monitor light curves, records of stellar brightness over time, looking for periodic dips caused by planetary transits. They study the wobble of stars, tiny shifts in radial velocity caused by a planet's gravitational tug. They also dissect the light spectrally. Using instruments called spectrographs, they spread starlight into a rainbow of wavelengths, searching for the faint fingerprints of atoms and molecules. In that spread, subtle absorption lines hint at planetary atmospheres. It is a delicate dance of signal and noise. Noise can come from instrumentation, from atmospheric turbulence, from the star itself. Spots on a star's surface, flares, magnetic cycles all can mimic or obscure planetary signals. You watch the data arrive. On a screen, lines curve and shift. Peaks rise and fall. Each point represents photons counted, recorded with extreme precision. At first, it looks like chaos. But slowly, patterns emerge. Periodicity. Dips at regular intervals. Spectral features that repeat across multiple transits. And when the signal stands out clearly, there is a quiet satisfaction. A world has revealed itself indirectly, invisibly, yet undeniably. You consider space telescopes like Kepler, TESS, and the James Webb Space Telescope. Kepler stared at one patch of sky for years, recording hundreds of thousands of stars. TESS scans nearly the entire sky, finding nearby planets suitable for further study. Webb, with its enormous infrared sensitivity, peers into planetary atmospheres, detecting chemical signatures that hint at water, methane, carbon dioxide, and other molecules. It is astonishing. Human hands, human minds, have built instruments capable of detecting the chemical composition of a planet orbiting a distant star. And you feel the intimacy of this work. In a way, the telescope tastes starlight, sampling the photons as a connoisseur samples wine. Every measurement requires calibration, understanding, patience. Every reading must be interpreted within a framework of physics and chemistry. You are reminded of something: technology does not replace wonder. It amplifies it. It allows you to extend your senses beyond the limits of your body, to perceive things no human could detect unaided. But precision is a slow companion. Observations take time. A single transit may last hours. Multiple transits are necessary to confirm a planet's existence and to refine estimates of size, orbit, and atmospheric composition. A single spectrum may be insufficient. Repeated measurements reduce uncertainty and separate faint signal from background noise. And yet, the process is meditative. Watching a star, analyzing photons, confirming patterns, it is rhythmic, deliberate, almost like breathing. Observation itself becomes a form of patience, a meditation on light and time. You think about the distances involved. A star 100 light-years away sends its light, unknowing, across the void. You capture it today. But that star, and its planets, are frozen in the state they were a century ago. Perhaps storms rage on their surfaces. Perhaps oceans ripple. perhaps life, if present, thrives or falters. You cannot see the present, you see the past. The telescope is a time machine as well as a sensor. And yet, you persist. You persist because every photon carries information. Every measurement refines understanding. Every confirmed exoplanet expands the horizon of possibility. You imagine the future. Telescopes larger than any currently in orbit, equipped with coronagraphs or starshades, will block starlight intentionally to glimpse faint reflected light from planets. They may detect surface features, clouds, even oceans. The chemical fingerprints will become clearer. Atmospheres will be read like letters written across light years. All of this begins with careful listening, with tasting the faintest signals, with instruments sensitive enough to detect whispers amid the roar. And in this quiet, technical marvel, you feel a gentle connection between human curiosity and the vastness of space, between photons departing distant suns and your patient attention, between the infinitesimal and the immense. It is a humbling realization. The universe does not shout, it whispers. And you, through ingenuity and persistence, have learned to hear it. As you stand beside these instruments, you also feel the responsibility of interpretation. False positives are common. Stellar variability, instrumental artifacts, cosmic dust all can deceive. Scientists must verify repeatedly, cross-check, compare models, and challenge assumptions. This patience is not frustration. It is care. Care for understanding. Care for accuracy. Care for truth. You think about the quiet moments when discoveries are made. Not with fireworks, not with loud announcements, but with subtle confirmation, a series of graphs, repeated observations, the alignment of multiple lines of evidence. A world appears in data first. Not in images, not in direct observation. It announces itself with a faint dip in light, a slight wobble, a chemical fingerprint. A delicate signal, carefully teased from the noise of the cosmos. And when the signal is confirmed, the celebration is quiet too, smiles exchanged among colleagues, careful notes recorded, and the world continues to turn. The telescope continues to watch. The photons continue to arrive. The universe continues its patient passage. Through these instruments, you begin to see that exploration is as much about listening as it is about seeing. About tasting the air of distant worlds through photons that have journeyed for decades or centuries. About turning curiosity into action, precision into discovery. And as you consider the telescopes stretching their mirrors toward ancient light, you realize that the search for planets and atmospheres is not noisy or chaotic. It is intimate, meticulous, and profoundly quiet. Every measurement is a whisper received. Every confirmation, a shared secret with the universe. And in that quiet, you understand that the next step, the interpretation of chemical signals, the search for life's fingerprints, will require the same patience, the same care, the same meditative attention to faint signals hidden in brilliance. Because the universe does not reveal itself all at once. It reveals itself in subtle ways, and only to those willing to wait, to taste its light, and to listen. And now, with telescopes poised and data arriving, you wonder what messages the next faint photons might carry, and what hidden worlds are yet to whisper their presence across the void. You have grown accustomed to signals, to spectra, to faint whispers of distant worlds. You have learned to detect chemical fingerprints in alien skies, to follow the rainbow of starlight through atmospheres, to imagine life hidden behind invisible veils. And yet, tonight, you sit with a gentle caution. Not every pattern is what it seems. The universe is not obliged to be honest. It plays tricks, subtle and clever, challenging assumptions at every turn. A false positive can arise easily, if one is not careful. You begin with volcanoes. A planet with active volcanism may release gases that mimic biological activity. Carbon dioxide, sulfur dioxide, hydrogen sulfide, all are products of geological processes. Methane can emerge from hydrothermal vents, without any hint of biology. You imagine a planet with bubbling lava flows and clouds of gas. Its spectrum shows oxygen or methane. At first, it might suggest life. But the origin is chemical, not biological. Geochemistry can be deceptive. High-energy ultraviolet radiation from a nearby star can split molecules in a planet's atmosphere, producing oxygen or ozone without life. Photodissociation can accumulate these gases over time, creating patterns that resemble biosignatures. You picture a red dwarf star, small and active, emitting flares that bathe a planet in ultraviolet light. Oxygen builds up in the thin atmosphere. Methane is scarce. A telescope from light years away detects the oxygen signature. Would the observer assume life exists? Not necessarily. False positives demand careful thinking. Even on Earth, history reminds you of caution. Before the discovery of photosynthesis-driven oxygen, scientists speculated about how oxygen appeared in the atmosphere. Without considering the balance of biological production and geological sinks, they could have misattributed the signal. The lesson is humility. Signals must be interpreted within context. They are pieces of a larger puzzle. A single detection, without corroborating evidence, is insufficient. Multiple lines of observation, repeated over time, are required. Confirmation is a slow process. You consider clouds. They scatter light, altering the apparent chemical signature. Hazes can absorb or obscure absorption lines. Planets with thick atmospheres or high-altitude particulates may hide their true composition. Without understanding cloud chemistry and distribution, you risk misinterpretation. You imagine the telescope capturing spectra through a hazy, alien sky. The absorption lines shift subtly. Peaks and valleys in the data appear, disappear, and reappear. Patience and repeated measurements are necessary to distinguish reality from illusion. Even stellar behavior can deceive. Starspots, cooler regions on a star's surface, can mimic the dips in brightness used to detect transits. Flares can produce sudden bursts of radiation that resemble chemical signatures. Stellar variability introduces noise that must be accounted for meticulously. It is a cosmic game of mirrors. And yet, these challenges are not discouraging. They are instructive. Each complication forces refinement of methods, development of better models, more precise instruments. Science becomes a dialogue not just between humans and nature, but among observers, data, and theory. You reflect on the careful protocols of verification. Observations are repeated, using multiple telescopes and instruments. Different wavelengths are examined. Atmospheric models simulate various non-biological scenarios. Each hypothesis is tested against evidence. The universe insists on patience. In this way, false positives serve as teachers. They reveal the complexity of planetary systems, the subtlety of stellar physics, the myriad ways chemical processes can unfold. They remind you that certainty is delicate. Evidence must accumulate before conclusions are drawn. You consider exoplanet atmospheres rich in oxygen. Alone, oxygen is intriguing but not definitive. Add methane, and the case strengthens, but even that requires scrutiny. Could the methane arise from geological activity? Could oxygen accumulate through photochemical reactions in a particular stellar environment? Each variable must be explored. The process mirrors life itself, iterative, cautious, adaptive. You imagine a distant planet whose atmosphere is entirely volcanic in origin. It produces sulfur dioxide, carbon monoxide, traces of methane. From afar, a telescope might detect these signals and misinterpret them as signs of metabolic activity. Yet the reality is geological. You imagine another planet, bathed in intense ultraviolet radiation. Water is photodissociated, hydrogen escapes to space, oxygen accumulates. It could persist for millions of years, creating a seemingly oxygen-rich atmosphere. The observer, unaware of the star's behavior, might suspect biology where there is none. Every potential biosignature carries the risk of misreading. You appreciate the delicacy of interpretation. To confirm life requires understanding the interplay of geology, chemistry, stellar radiation, planetary mass, and atmospheric dynamics. It requires context. It requires cross-checking and skepticism. You also appreciate the subtle beauty in these false positives. Each scenario teaches you about planetary diversity. Each chemical imbalance, even if not caused by life, tells a story. Some worlds are volcanically hyperactive, some are irradiated by restless stars, some are frozen or molten beyond imagining. Science becomes an exercise in patience. Observing, testing, simulating, and verifying. One dataset leads to another. Hypotheses evolve. The story of each planet emerges slowly, carefully, like dawn over an alien horizon. You realize the virtue of uncertainty. To move carefully, to verify, to allow room for error, is to honor the complexity of the cosmos. The universe is generous in its lessons, but demanding in its precision. And yet, amidst caution, there is wonder. Even false positives reveal hidden worlds, intricate chemistry, dynamic atmospheres, and possibilities you could scarcely imagine. They remind you that every observation, confirmed or misleading, expands your understanding. You let the quiet settle. The search for life is a dialogue, not a declaration. Each spectrum, each absorption line, each dip in starlight is part of a conversation. You listen. You interpret. You test. You wait. And sometimes, the universe whispers a truth that is subtle, almost shy, a hint, a pattern, a clue rather than a bold announcement. You breathe gently. You think about the care required to interpret these messages. And you reflect on your own world, Earth, where the interplay of life and chemistry has persisted for billions of years, producing signals that could be detected from light years away. It is a delicate balance. A whisper maintained through countless cycles of geology and biology. You feel a growing respect for the patient labor of observation. For the insistence on cross-checking. For the quiet, careful accumulation of evidence. False positives are not failures. They are reminders that certainty is precious and rare. They teach you to question assumptions, to seek deeper understanding, and to cherish clarity when it arrives. And as you consider distant atmospheres, you wonder, when the true biosignature appears unmistakable, persistent, and unambiguous, how will you know it is not another cosmic trick? The answer, you realize, will not be in a single spectrum, a single telescope, or a single moment. It will emerge from patience, from accumulation, from careful listening. And in that realization, you feel both the fragility and the strength of scientific discovery, poised between doubt and awe, ready to follow the faintest traces wherever they lead, into worlds yet unknown. You pause and consider the journey of light. Every photon that reaches your telescope, every beam that enters your eyes, has traveled vast distances before it finds you. Across the void of space, through emptiness and time, these photons carry the story of a star, a planet, a moment in a cosmic history you cannot otherwise witness. You are not seeing a planet as it is now. You are seeing it as it was when that light first departed. Sometimes that moment was a century ago, sometimes millennia, sometimes millions of years in the past. Every observation is, in a way, a window to history. You think of a star 500 light-years away. Its light left the star 5 centuries ago. While it traveled, civilizations could have risen and fallen. Geological events may have reshaped its planets. Atmospheres may have evolved, oceans may have formed or evaporated. And yet, the light you detect remains fixed in its ancient pattern. Time becomes inseparable from distance. Each signal is a memory delivered late, a message from the past arriving in the present. You consider the photons you have just measured, their wavelengths encode the composition of an atmosphere, hints of chemical imbalance, subtle indications that life might exist. Yet all of it is frozen in history, a cosmic photograph taken before you were born. This is both humbling and awe-inspiring. To search for life on exoplanets is to trust in the patience of light, to interpret a message carried across centuries. You cannot hurry it. You cannot rewind it. You can only observe, carefully, and imagine what might now be. The finite speed of light sets a quiet rhythm to discovery. A planet orbiting a star 1,000 light-years away is already 1,000 years removed from its current reality. Perhaps life has arisen there, perhaps it has perished. Perhaps its atmosphere has transformed entirely. And you will only know the moment the next photon arrives, centuries later. You feel the vastness of these distances. Light years, those almost unimaginable stretches, are not just measures of space, but of time. Every step across the galaxy stretches your awareness of patience, of perspective, of cosmic scale. And yet, despite this immense separation, a connection forms. Through careful observation, you touch these worlds. You detect their chemical fingerprints, follow their light curves, infer their motions. The universe speaks to you across the void. You interpret. You imagine. You understand. You dwell for a moment on the elegance of it all. Light, though intangible, is a messenger, a courier of information. It carries with it energy, color, time, and space. From the tiniest photon, traveling billions of kilometers, you can deduce the presence of an atmosphere, the size of a planet, the orbit of a moon. You can glimpse hints of water or methane, signatures of possible life. The stars become storytellers, their light narrating the past in spectral lines and shifts. Every transit, every wobble, every subtle dimming is a sentence in a story written long before your instruments existed. And you are learning to read it. You imagine planets orbiting these distant stars. Their landscapes frozen in the light you observe. Oceans ripple gently, clouds drift across alien skies, perhaps winds stir, perhaps volcanic plumes rise. You see it as it was, a snapshot preserved in photons, and wonder at the unfolding history that continues unseen. Some signals take millennia to arrive. You imagine observing a planet whose star went supernova hundreds of years ago, the light continuing toward you, carrying chemical imprints of a world that no longer exists as you see it. And yet, for a moment, that planet lives again, in the photons that reach your instruments, and in your mind as you interpret them. Time is stitched into your observations. You reflect on the human aspect of this endeavor. Scientists begin measurements, collect photons, analyze data, sometimes waiting decades for confirmation. By the time a planet is confirmed, entire careers may have passed, technology may have advanced, understanding may have deepened. The universe requires patience, and humanity complies, slowly and deliberately. You also consider how your perspective is shaped by this delay. You are always seeing the past. Every exoplanet's light is a whisper, a historical record. If life exists there, it may have evolved or vanished since the light began its journey. The universe reminds you of impermanence, of the transient nature of existence, even on planetary scales. And yet, in this temporally stretched observation, there is clarity. Ancient light carries unaltered information. No human presence can interfere with it. It is pure. It is honest. It reveals the state of a world as it was, unfiltered, unedited. You think about the implications for the search for life. Confirmation, interpretation, and understanding must all account for time. You cannot assume that an atmosphere you detect today is exactly as it is in the planet's present. Chemical processes may have altered it, life may have arisen or vanished, geological events may have reshaped it. Still, every photon is an opportunity. Every observation is a chance to glimpse patterns, to identify disequilibrium, to consider the potential for life. Even if the information is delayed, it is meaningful. You marvel at the patience required, not only of photons but of observers. Science here is both slow and precise. Confirmation often requires repeated transits, multiple wavelengths, corroborating observations from different instruments. You cannot rush the universe. You must wait, as the light arrives, as the signals accumulate, as understanding grows gradually. The distance between worlds teaches humility. What you see is never the full present. You observe, interpret, and imagine. You reconstruct, with care, the story encoded in ancient photons. The universe keeps secrets, but it offers clues. And if you are patient, it whispers them to those who listen closely. And yet, despite the distance and the delay, a profound intimacy forms. You feel connected to these distant planets. Across centuries and light years, across emptiness and time, you participate in a dialogue with worlds that cannot respond, yet speak through the medium of light. You read their histories, infer their states, and contemplate their possibilities. You let yourself reflect on the fragility and persistence of this information. Each photon is irreplaceable. Each measurement is a gift. The stories they tell are snapshots, finite, precious, waiting to be interpreted. You breathe, slowly. You feel the tension between distance and understanding. Between past and present. Between what exists and what you can perceive. Somewhere, across the galaxy, planets orbit stars whose light began traveling before your own parents were born. Perhaps civilizations have risen there. Perhaps oceans churn. Perhaps life flourishes, perhaps it has ended. You cannot know, not yet. And that is part of the wonder. The delay is not frustrating, it is a meditation. Every discovery is a reminder that knowledge is patient, cumulative, and slow, and that every photon carries within it the memory of time itself. You close your eyes for a moment, imagining the journey of those photons. From star to telescope, from past to present, they carry stories waiting for comprehension. Each exoplanet becomes a memory arriving late, a message from the cosmos, a whisper from worlds long unseen in your time. And as you open your eyes, you feel the quiet anticipation for what comes next, for the interpretation of chemical signals, for understanding disequilibrium, for sensing whether life itself might have left a signature in that ancient light. Because even after traveling hundreds of years, the universe is patient. And you, learning to listen, are patient as well. Somewhere, in the light that reaches you tonight, a planet continues its orbit, unaware that you are observing, and you wonder what it has become in the centuries that have passed. You have followed light across centuries. You have watched distant stars, measured subtle dips, tasted the spectra of faraway atmospheres. You have learned to distinguish the delicate signals from the noise, to separate the whispers of planets from the roar of their suns. And now you imagine a moment you have long anticipated, the atmosphere itself speaks back. It is not shouting. It is not a comet blazing across the sky. It is quiet. Precise. Persistent. A pattern emerges in the data. The combination of molecules is unusual, unlikely to arise without life. Oxygen and methane coexist in disequilibrium. Carbon dioxide fluctuates alongside other gases in ways that suggest active cycling. There is no other plausible explanation. This is not geology. This is not photochemistry. This is life, or at least, the signature of life. You imagine the first confirmation. Perhaps it is a graph, a spectral line with a clarity you had only hoped for. Perhaps it is repeated across multiple transits, across different instruments. The signal is unmistakable. Persistent. Real. Your mind stretches to comprehend the implications. A world, light years away, has chemical breath. Its atmosphere is alive with processes that cannot occur by chance alone. Something, somewhere, is altering its environment in a way that suggests sentience, or at least biology. The thought is both exhilarating and quieting. You do not cheer. You do not leap. You sit and absorb the magnitude. The air itself has spoken, and you have listened. You think scientifically first. Confirmation requires rigor. Multiple measurements. Cross-checks. Models. Peer review. The stakes are enormous. You cannot jump to conclusions. The universe is subtle, mistakes are easy. Yet the pattern is consistent, and every test strengthens confidence. You consider the philosophical weight of this moment. Life exists beyond your planet. It is not hypothetical. It is not confined to imagination. Somewhere, the chemistry of existence has found a foothold. Somewhere, the balance of molecules, the cycling of energy, has produced a phenomenon that mirrors what you recognize as living processes. You imagine the spectrum of possibilities. Microbial life in oceans beneath clouds, releasing gases into the atmosphere. A biosphere thriving on chemical gradients, cycling energy in ways you have only begun to model. Perhaps it is simple. Perhaps it is complex. Perhaps it is beyond your comprehension entirely. And yet, this realization does not diminish your own world. It enhances it. You think of Earth as a participant in a larger cosmic conversation. Oxygen you inhale, carbon dioxide exhaled, methane rising from wetlands and permafrost, these are the markers of life you release into space. Somewhere else, life may be doing the same. Somewhere else, a planet breathes in rhythm, slowly and persistently, across light years, and you can detect it. The moment is quiet because it is profound. There is no sudden fanfare in the universe. No trumpet sounds. Only photons continue to arrive, now carrying the affirmation of life. You consider your place in this web of existence. To confirm life elsewhere is not to diminish humanity. It is to expand understanding, to see that the processes that produce life are perhaps not unique. That chemistry, under the right conditions, can awaken into biology. And yet, you feel a shiver of humility. How much more is unknown? How many planets have you overlooked? How many world signals are faint, just beyond the reach of current instruments? The universe is vast, and confirmation of one biosignature is but a single note in a vast symphony. You imagine the reactions of humanity. Quiet reflection, rigorous analysis, ethical debates, philosophical discourse. Questions of meaning, of purpose, of responsibility. What does it mean to know that life exists beyond Earth? How do you define alive when confronted with the alien? How do you prepare for the potential communication of a biosphere, however indirect, across time and distance? And yet, the moment is deeply personal. For you, standing beside instruments that taste starlight, the confirmation is an intimate revelation. You have listened patiently, interpreted carefully, and now, finally, the atmosphere speaks. It is a reminder that life is not a local phenomenon. That the universe can and does produce complexity, persistence, and patterns that resemble your own. You reflect on the quiet patience required to reach this point. Years of observation, analysis, theory, and revision. Mistakes, false positives, misinterpretations, all part of the path to understanding. And now, after all that care, clarity arrives. You think about Earth's own atmospheric signature. Oxygen, methane, and other biosignatures persist because life continually renews them. The balance of these molecules is a product of living systems. To recognize the same patterns elsewhere is to recognize the same dance of life, in another time and place. And it is subtle. You do not hear a roar. You see the evidence. You measure the imbalance that cannot be explained otherwise. You witness the persistence of disequilibrium, a hallmark of life itself. You imagine yourself standing beneath the night sky, contemplating this distant world. Its light has traveled centuries to reach you, carrying chemical whispers that confirm something extraordinary. Somewhere, the air itself is alive, speaking across the void. You consider the possibility of observing more than one world. A galaxy dotted with planets, some dry, some icy, some molten, some breathing in their delicate atmospheres. How many signals await discovery? How many patterns hint at life, yet remain undetected because your instruments are not sensitive enough, or because the light has not yet arrived? You breathe slowly. The magnitude of this realization fills your mind gently, like a soft current. You are part of a process that transcends time and distance. You are listening to the universe, learning to read its subtle language, and finally, the universe replies. The moment is profound in its quiet. You do not need noise to know significance. The signal is its own announcement. The air has spoken. And you, attuned and patient, have heard. You pause to let the stillness settle. You feel reverence for the science, for the patience, for the clarity that has emerged. You recognize the delicate dance that brought you here, technology and human curiosity intertwined, reaching out across the cosmos to witness life beyond your own planet. And as you exhale, you feel the inevitability of the next step. Confirmation of life in a distant atmosphere is only the beginning. Interpretation follows, understanding of its complexity, consideration of its origin. Questions of similarity and difference arise. Philosophical, scientific, personal questions ripple outward like the waves of light that brought you this message. You sense the stillness before an answer. The universe has whispered, and you have listened. Yet the story is not complete. The light carries only the present moment frozen in time. What follows, what emerges next, remains unknown. And so, in the quiet of your observation, you prepare to follow the next signal, to read the next spectrum, to continue listening to the air that speaks across the void, waiting for the next subtle message that life, somewhere else, exists. You slowly turn your attention homeward, carrying the weight and wonder of distant worlds with you. After tracing photons across light years, after listening to the faint whispers of atmospheres far away, you arrive back at your own planet. You feel the gravity beneath your feet, the air brushing your skin, the rhythm of your heartbeat and breath. And in that gentle return, you realize something profound. You are not just an observer. You are also part of the cosmic conversation. Earth itself is a signal. Every breath you take, every wave that laps ashore, every rustling leaf and humming insect contributes to the orchestra of life. Your planet radiates light, heat, radio waves, magnetic disturbances, and chemical patterns all traveling outward into the void. If someone were listening, far across the galaxy, they could detect your presence. You imagine a distant telescope or sensor catching traces of your oxygen-rich atmosphere. They would measure the constant imbalance of oxygen and methane, a chemical signature that persists only because life renews it. They would detect water vapor cycling through clouds, seasonal variations in vegetation reflected in light, and the delicate warmth of a planet with liquid oceans. The world hums with activity, and the universe may be attentive. You inhale slowly, letting the idea settle. You, and all of life on Earth, are leaving a spectral fingerprint. It is not loud. It does not announce itself with fireworks. It whispers gently, as photons depart, as molecules escape into space, as radio waves ripple through the atmosphere. You realize that in seeking life elsewhere, you have been measuring reflections of your own existence. The same principles apply. Patterns in light, in chemistry, in radiation, can reveal a living world. Life, wherever it arises, produces signals. Life interacts with its environment, leaving traces in ways both subtle and profound. And so, in observing distant planets, you have also been observing a mirror. A reflection of your own planet's vitality, your own role in a larger cosmic story. You consider the rhythms of Earth. The planet breathes with you. Photosynthesis converts sunlight into chemical energy, producing oxygen as a byproduct. Volcanoes release gases that cycle through the atmosphere. Oceans moderate temperature. Clouds reflect light and trap heat. The biosphere dances with the planet, balancing, shifting, persisting. From space, these rhythms create patterns, detectable even across light years. You could, theoretically, measure the spectrum of Earth and see the fingerprints of life as distinctly as you do for other worlds. You feel a gentle humility in this realization. Your planet is not just a backdrop for human activity. It is an active, dynamic participant in the universe's story. It is alive in subtle, measurable ways. And through the act of observation, through instruments both biological and technological, you are part of that signal. You imagine an alien civilization, perhaps at a distant star, doing exactly what you have done. They trace photons back to a small blue planet, measure chemical imbalances, and detect the presence of life. The same curiosity that drives you, drives them too. Across vast distances and unimaginable time, life recognizes life not by voice, not by sight, but by signature. This thought brings both connection and quiet wonder. You are not alone in consciousness, for wherever life arises, it leaves evidence. Wherever life persists, it reaches outward, intentionally or inadvertently, into the silent cosmos. You contemplate the messages your planet sends unintentionally. Radio transmissions, television signals, signals from satellites, energy usage detectable as heat, even subtle vibrations of the Earth's magnetic field. These are all part of the complex signal of human activity, superimposed upon the natural rhythms of the planet. If someone were listening carefully, they might detect you, piece together the story of your civilization, long before you were aware of theirs. And yet, you are still patient. You understand that detection is subtle, dependent on distance, orientation, and the sensitivity of observation. The universe is vast. Your signal, while persistent, is faint. It travels across empty space, scattered and diluted. But the potential is there. Life is always communicative, whether deliberately or not. You reflect on your own role as an observer and a participant. In listening to distant exoplanets, you learn not only about them but also about your own planet. Patterns you detect elsewhere are reflections of principles already present here: chemical disequilibria, climate cycles, atmospheric dynamics, interactions between living and non-living systems. You understand that Earth is a laboratory of life, continuously sending out proof of its existence. From the perspective of a distant observer, your world might appear to pulse with vitality, a signal to be read and interpreted. And you, standing on the surface, are a conscious extension of that signal. Your curiosity, your instruments, your interpretations are part of the story you emit. In observing, you also participate. In measuring, you leave traces of intention. In seeking, you connect the act of life with the act of discovery. You imagine a night sky where countless worlds are similarly broadcasting their existence. Each planet is a signal. Each biosphere, if present, is a subtle beacon. Some are quiet and unchanging. Some fluctuate with the seasons, the evolution of life, the dynamics of atmosphere and geology. Some may already have disappeared, leaving only photons in transit toward another observer. And you feel a profound continuity. Across space, across time, across the diversity of worlds, life persists and communicates, even unintentionally. The cosmos is a library of signals, and you are both a reader and a contributor. You think of the profound interconnectedness this implies. That the search for life elsewhere is, in a sense, a reflection of your own existence. That every discovery of a planet, every spectral signature, every possible biosignature is a reminder of your own significance, and the universality of life's capacity to leave traces. You breathe gently and imagine your planet as seen from afar. Oceans glint in reflected starlight. Clouds drift in delicate currents. Forests, deserts, ice sheets, cities, all contribute to the subtle signatures radiating outward. Life pulses quietly, persistently, consistently, a signal across the void. And in this reflection, you recognize a gentle invitation to care for your own signal. To nurture the balance of life, to preserve the chemistry that makes detection possible. In seeking other life, you realize that sustaining your own is part of the cosmic dialogue. The earth, your body, your breath, all resonate in the same frequency of existence. You are not separate from the universe you study. You are embedded within it, both reading its signals and sending your own. And as you exhale, you feel the warmth of your own presence on this planet. The signals you emit are subtle, but real. The light you reflect, the gases you release, the energy you generate, they all carry information outward. Somewhere, perhaps, someone or something may detect it. Perhaps a distant observer is reading the spectral fingerprint of your world right now, just as you have read countless others. You close your eyes for a moment and imagine the delicate connections across space. You are both an observer and a participant, part of a continuum of life that leaves marks upon the universe. Every breath you take, every wave, every leaf, every photon, a part of a signal traveling outward, across the emptiness, toward potential understanding. And as you inhale again, you sense the cycle: life observes life, light carries life, knowledge reflects life. The search for exoplanets, the study of atmospheres, the pursuit of biosignatures all lead back, in the quietest, most intimate way, to the recognition that you are already speaking, already detectable, already part of the ongoing cosmic conversation. Somewhere in the vast darkness, the universe is reading you, just as you have read it. And in this gentle awareness, you find comfort, connection, and the quiet wonder of being alive.